Where were we? Let's first go to the previous lecture and let's just revise what we have been doing. So in some sense, this sort of takes us, what we are doing now takes us sort of to the unnatural endpoint in imitating what you did last semester as far as differential calculus was concerned, which is to find maxima and minima. And so we have the analog of the second derivative test. So let us just assume that the functions are sufficiently differentiable. So C3 is enough. So in that case, what do we know? We know that if I have, for a function that is defined on an open set in Rn, a real valued function, if I have a local maximum or minimum at any point, then because the derivative exists, we know that the derivative has to be zero. This tells us that in order to look for maxima and minima at for such functions defined on an open set, it is enough just to look for points where the derivative is zero. Now we want to classify these points. Is it a maximum? Is it a minimum? Or is it neither? And for that, we look at the second derivative. So we know that if I have a local minimum, then the second derivative has to be positive semi-definite. Remember that the second derivative is encoded in the Hessian matrix, which is all the second partial derivatives. And because the function is assumed to be C2, this matrix is symmetric. In particular, it has all its eigenvalues are real, and it can be diagonalized by means of an orthogonal matrix. Anyway, so we know that if the critical point happens to be a local maximum, then the double derivative, this matrix is negative semi-definite, and for a local min, it has to be positive semi-definite. If the matrix is singular, that is, if it has 0 as an eigenvalue, then I cannot really turn this around. Looking at the one variable situation, we know that x cube, x to the 4, and minus of x to the 4, at the origin, the double derivative is 0 for all of them, but the critical point is different, right? So we assume that, but if we assume that the Hessian is non-singular, then actually the second derivative can allow me to classify the critical point. So what is the upshot? That if I have a critical point, which is to say that the derivative is 0, the 0 operator, and if the Hessian is non-singular, then you have obtained a local minimum if and only if the Hessian is positive definite. And you have a local, did I say that right? I have a local minimum if and only if the Hessian is positive definite. I have a local maximum at this critical point if and only if the Hessian is negative definite. And a new phenomenon that I see for the multivariable situation is that if the Hessian is non-singular, but if some eigenvalues are positive and some are negative, then this is a mixed type of point. In the directions in which, in an eigen direction, if you will, where the eigenvalue is positive, if I travel in that point, then I know. Yes.
So you have to record.
All right. So yes. I will start recording. Let me just finish this thought, and then we will. So we know that if we are going in a direction in which the eigenvalue is positive, then the graph in that direction, it's a one variable situation now. Because the eigenvalue is positive, I will have a local minimum in that direction. But in another direction where the eigenvalue is positive, getting mixed up, where the eigenvalue is negative, in that case, I will have a local maximum. So I get a saddle point. And okay, so let me start recording here.
Recording in progress.
All right, so for functions that are sufficiently differentiable, we have now this test of how to detect possible local maximum or minimum Namely, those have to be critical points if the function is differentiable at that point and it's an interior point. And then we have the second derivative test to detect if it's a local maximum or a local minimum or neither. That is, if it's a saddle point, namely a maximum in some direction and minimum in some other direction. This test is available to us if the Hessian, which is the matrix that encodes all the double derivatives at that point, all the partial double derivatives, whether if that matrix is non-singular, then I can tell. Okay, so today we are going to apply this. But more generally, or rather in a complementary way, we will see that there is a lot of geometry that is associated with the various calculations that we are able to perform. So let's see a bunch of examples, right? Okay, so this is all from last time. And at the end, I gave you a bunch of examples. Okay, so this is where we found out for a general quadratic polynomial of a number of variables, which I have encoded it in this form, and I called it phi of x. We did the calculation about how to tell, how to find out critical points and how to classify them. So just to see, if we assume that the Hessian is non-singular, then there is a unique critical point. And then, and the Hessian then is just going to tell us whether the critical point is local maximum or minimum or a saddle point. All right, so let's come to examples. So these are the examples that I wrote down last time. So let us see the geometry behind these examples one by one. Okay. Let's just continue below this time. And okay, so let's take a look at these. So if my function quadratic, so for now we are going to concentrate just on quadratic polynomials. If this quadratic polynomial is of n variables, then I have a real valued function of n variables. So its graph will be drawn in dimension n plus 1. So if n is 2, then I have a function of x and y, and then the z coordinate is going to record the value of the function. So I will get some kind of surface. Let's try to understand the geometry of this surface in simple examples. And one way in which I can do this without going to 3 dimensions is the familiar tool in geography of drawing contour diagrams. So I have a 2D map, but I just connect all points at the same height by means of a curve. And if I color code these curves, then I can visualize the heights. Okay, so let's do this for simple examples. And other examples. Okay, so let us say I have this function of n variables is in Rn plus 1. I can visualize it in Rn by drawing contour diagrams, or we call them level sets. Namely, plot phi of x1 up to xn equals c for various values of constant And this plotting is going to happen in Rn, plot in Rn. So let's see examples of this. So look at, so above I have x square plus y square. Let's just take those. Okay. So examples. F of xy equals x squared. So this is a function of two variables, but it depends only on x. All right. So, so we will draw the graph of this in 3 dimensions very soon. But how about the contour diagrams? So this is going to, these are contour diagrams are going to be drawn only in 2 dimensions. And this is the x-axis, this is the y-axis. So the function does not depend on y at all. So no matter what the value of y is, for any fixed value of y, for any fixed value of x, the function is going to be constant. So let's plug in x equal to 0. That means on the y-axis, what will be the value of the function? Come on. So here the function is going to be 0. And so that means I just plot this as a level set. So here, so this is the level set 0. Okay. So when x is 1, what is the value of this function?
1.
Again, it's going to be, yeah, so it's going to be 1. So this is the level set for 1. But for 1, I have another one, which is at -1 also, the value is going to be 1. And so maybe I should start color coding this. What if I take, so looking at the example, what if I take C to be 4? So if I take C to be 4, then the value of x is going to be 2 or -2. Right? So x square is equal to 4. So this is going to happen. So I'm just going to draw x square equals 4. So the graph of that is 2 parallel lines, namely when x is equal to 2 and when x is equal to -2. Right? So these red lines I have to label with not 2, but with 4. And as I go further and further out, I'm going to get parallel lines that get further and further apart. Okay, so it's a very simple thing. And can we draw this in 3 dimensions? Let me make an attempt. The graph is very simple. So let's say this is the x-axis and this is the y-axis. What is the picture going to look like? Well, it's as if you take a sheet of paper and you just fold it. I mean, not fold it, but bend it. So something like this. Okay, so in profile, I'm going to draw something like this. Okay, already it has gone bad. Okay. And the z-axis is up here. Okay. This is x, this is y, and this is the z-axis. Okay, so not particularly exciting. I should draw this here. So of course, this is going to be something that extends infinitely up, and then it extends infinitely along the y-axis in both directions, right? But I have just cut that in order to show the shape. Okay, so this is one example. What if I take second, which is f of xy equals x square plus y square, and what will be the level sets here?
Circles.
Exactly. And
Circle centered at the origin.
Centered at the origin. So level sets circles centered at 0, 0. So let's draw the diagram here. So of course, this is also going to be a level set, and the level of that will be 0. Then this is a level set, which is at level 1, where this is 1. And if I draw a circle with double the radius, so if I can get this right, maybe not. I think I'll let the visual description speak for itself. How will the graph look like in 3D?
This is actually the surface of revolution of the parabola.
Exactly, right? So it's going to be a paraboloid. Right? So let me see if I can draw this. And soon my drawing skills will be overwhelmed. So at that point, we will have to see it on the screen. So in the same way, I have this X and I have the Y. And maybe something like this. Let's use and of course, to attempt to give it some kind of depth. So that's what the picture is going to look like. If I put a minus sign in front of this, then this thing whole simply will turn upside down. It will go to the negative x-axis. Okay, so now let's get slightly more. What if I take f of x comma y equals let's say x square minus y square. What now? So let's draw the level sets. So if I have c equal to 0, then what do I get? That simply means
two lines.
Yeah, exactly. So I have to set this given formula equal to various constants, the c. So I'm setting c equal to 0. That means I have x square minus y square equal to 0. That just means x is equal to plus or minus y. So I get 2 lines. Or y equals plus or minus x. All right. So let's c is equal to 1. That tells me that x square minus y square equals 1. And let's say c equals minus 1. That tells me x square minus y square equals minus 1. Okay, so let's draw. Let's draw these level sets. You know what? Let's not draw the axis. Or perhaps draw the axis as dots. Okay, so x is equal to plus or minus y. So that is the first one. That is this. This is a level set. Passing through the origin. That's what is intended. Let me see if I can get it right. At right angles and passing through the origin. Okay. What happens if I take this second one? So I start color coding these. So this is 1 and this is minus 1. Oops. Here. So let's call this 1 in. Let's call this minus 1. Okay. All right. So what happens? Where is the red curve going to go? X square minus y square is minus 1. And that means that x square is going to be less than y square. Or in particular, I can just plot some point over there. I can have x equal to 0 and y equals plus or minus 1. So there will be a point here and a point here. But in fact, what is the graph going to be? X square minus y square equals minus 1.
A hyperbola.
It's a hyperbola. A hyperbola that opens up and down, correct?
I guess.
Because x square minus y square is negative, so y has to so y absolute value of y has to dominate that of x. So I'm going to have something like this. Go like that. Oops. So my poor drawing skills and inability to use this trackpad well, so they are both going to come together to make it bad. But anyway, something like this. And then the blue one will be on the other side. So there it will go through this, and I'll have something like that. Okay, what happens if I change the values? If I change the value more than one, what will happen to these level sets?
They will just move away from origin.
They'll just move further and further away from the origin. Okay, so now this is kind of interesting here. In that, how do we visualize this in 3 dimensions? So just take a moment until I label this. So this is 1. This is -1, and this is 0. Okay, so observe the following in light of whatever we said. If I travel along,
excuse me, sir.
Sorry, say that again, please.
Yes, sir. So along the x is equal to 0 plane, we'll have a parabola because f of 0 comma y is minus y squared. And likewise, when y is equal to 0, along the y is equal to 0 plane also we'll have a parabola. So origin sort of acts like a saddle shaped point.
Right. So let's see this by traveling along some directions. Okay. So if I travel along the x-axis, what happens? As I start coming from minus infinity, I'm going to have these blue curves, right? But the levels of those blue curves are going to keep on reducing, right? Until it comes to the drawn blue curve where the level is 1. And then it keeps further reducing until I become 0. Correct? So if as I come from this, as I come in this direction, so in this direction, so let me color this. In this direction, I start from infinity to 0 to infinity, correct? So in this direction, what do I have at the origin? A local come on. So as I travel along the x-axis, I have a local minimum at the origin at 0, 0. But of course, if I go to the y direction, what happens?
Get a local max.
I get a local maximum. I come from minus infinity, then I climb up to 0, and then I go to get local.
Actually, sir, wouldn't it be the other way around? Because if
is it the other way around?
oh, sorry, not yeah, never mind. Yeah, it's
because see the numbers that are written over there, they are the levels. So blue things are higher than blue things come above the plane, and red things go below the plane. Yeah, but you see, to visualize this becomes not that easy, right? So let's see this. Right. So let me see if I can.
So because you have the x squared and the y squared terms, like each being, like if you leave the other one constant, each of them in fact is just a parabola, right?
Yes.
So it might be easier to think about it as like the cross sections, right? At least if you look at it in terms of y, the cross sections are all parabolas and their heights are changing, right?
Okay, okay, all right. Let's look at the graph though, because there will be various ways of thinking of this. So let me see if I can just get this. Yeah, so 1 second. Okay, let's see if all right. So can you see this? Can you see the screen?
Yes, sir.
All right. So you see, this is just something I found online, and still haven't played a lot with it, but it's pretty nifty. So the surface is x square minus y square, and you see you can play with it. So the x direction is going from left to right, and the y direction is going into the screen as you travel in the positive direction, and z is up. So you see, as I travel in the y direction, I see that I have a local maximum as I go into the screen. But if I move from left to right, then you see I have a parabola and I get a local minimum. And you see, you can sort of play with this and see exactly what is going on. So with this, you can see why it's called a saddle, right? If you can sort of visualize what a saddle looks like on a horse. And yeah, so you can sort of play with these things. And I encourage you to, find whatever software you like and play with the various examples that we are going to do. Pretty neat. So, okay, so let's go back and see more examples. And the next example. So you see, here's sort of one way. If you think of yesterday's lecture and the way we encoded this, the way this ended up encoding in terms, how the Hessian turned out, then what you can say is that the coefficients of these squares of the variables, they are the things that are going to come along the diagonal, maybe multiplied by 2 when I take the Hessian, right? Yeah. So for x square, it is going to turn out to be, if I look at just the coefficients of how this polynomial is going to be encoded in terms of a matrix, the quadratic part, then the square terms, their coefficients will come along the diagonal, and the cross terms, things like xy, which we have not introduced so far, they will come as off diagonal entries, and the matrix will be symmetric. I hope you see what I'm saying. Okay, if that is the case, ignore the situation where I have cross terms. Then you see the coefficients of these the squares of the variables, they're just going to be the diagonal terms. So I can think of those as the eigenvalues of this diagonal matrix. And then you see what is going on. In the x square case, the two eigenvalues are 1 and 0. In the next case, I have 1 and 1. And in the last case, I have 1 and minus 1. And sure enough, in the case 1, 1, I have a positive definite matrix, and I got a minimum. In the case where I had 1 and minus 1, I have a positive as well as negative eigenvalue, and so I got a saddle. So let me just write this here. Okay, so while I'm writing this, the next example is the simplest example where I have a cross term. So just think about it. Just the graph of f of x comma y is equal to xy. Okay, so just think about it. And what's the idea here? I mean, we can start drawing the level here. So let's do that. Why not? Now that itself is a level curve, right? Namely 0. But then if I take 1, then I get the usual head, right? So this is for 1, xy is equal to 1. And if I take larger and larger values, then it will move away from the origin in both directions. And if I go with -1, then I get this. So what's the idea? Yeah, it's a totally different formula, but really, in some ways, this is exactly the same as example number 3, right? You just turn it
But
around.
the coordinate axis are just turned around.
Correct, exactly. So we will see that we can do this in general and get rid of these cross terms. But here, let us do this explicitly because it's easy enough. So here, so xy, I can think of it this as, so let us say, let's say the following. So I'm going to make a substitution. Oops. Let's say that u is equal to x plus y and v is equal to x minus y. So now, except, you see, what I would like to do is that, so I'm going to change basis here, right? Except when I change the basis, I really would like it to be an orthonormal change of basis. That means I would like the new vectors to have the same lengths. So if I'm going to let u to be x plus y, that means really as a basis vector, it is the old basis vector 1, 1, correct? Then I should scale it, right? So scale it by what? Come on,
By root 2.
Exactly, root 2. And then this is root. And in this case, you can just verify very quickly that x is going to be, I can express this, the reverse by what? I have to do u plus v, and that will give me times root 2. So it's going to be the same thing again, right? So this is also going to be divided by root 2 and y is equal to minus 2. Please check that I'm not making any mistakes. And in that case, what does xy turn out to be? It's simply going to be the product of this u plus v times u minus v divided by whatever. So this is u square minus v square divided by 2. And so you see that this is exactly the same as before, except for this factor of 2. So we are going to learn to do this in general. All right, so this is okay. So these examples may seem like very simple examples, like too simple, but we will see that we can, in general also, we can do exactly the same. All right, so we can say that we can visualize the graph of a general quadratic. Let's use yesterday's notation. Phi of x, which is really phi of x1 up to xn. So remember, that was, we had ai times xi square plus there was a matrix of AIs, right? So the diagonal entries were AII times xi square, and then the off diagonal entries, I put in a factor of 2. So this is what we have. X transpose AX plus some P times X. So P is a row vector, X is a column vector, plus R from yesterday. We can visualize the graph of a general quadratic by looking at its level sets. And what will the level sets be? That means I set this phi of x equal to some constant. And I vary the values of this constant. But the constant can be absorbed in this r at the end. And so effectively what this means is that I should be able to visualize the graphs of things of the type phi of x equal to 0. So should understand. So for this, we should understand graphs of these quadratics and quadratic hypersurface of the type phi of x equal to 0. So inspired by what we did earlier, let me try to justify that what I said earlier. So you see, the examples that we had, they were very simple, right? Just sums or differences of squares, maybe with some coefficients. And then we saw that xy, I was able to transform into that. So this simple form we will call a standard form. And we will show that any graph can be really reduced to the standard form just by very simple manipulations. Where x is a quadratic polynomial in n variables. So the standard form of this is, let's say, lambda 1 x1 square plus up to lambda n xn square. Let's say plus some constant. Plus constant. And of course, it is understood that this is equal to 0. So this is, let us show that I can always reduce to this form. So we will see that by a shift of origin and orthogonal we can express any general, of course, quadratic. So let me just say, to be absolutely clear, any general okay. So first we will do the sort of an easy part, which is the shift of the origin. And so what that effectively allows us, so let's work backwards. If I do a shift of origin, and you have seen this in school, that if I have a graph, let's say y equals f of x, and if I just plot the graph of, if I put x minus 2 for x in that graph, what happens to the graph? Very simple. If I draw the graph of x squared, then it is something. If I draw the graph of x minus 3 the whole square, how are the two related?
You shift it right by 3 units.
Yeah, so you shift x square right by 3 to get x minus 3 the whole square. And if I add 4 to the whole thing, then I shift it up, right? So it's just, I've just shifted the origin from 0 to 3, 4, etc. So if I do the same thing over here, let us say each of the xi's, I put an ai, subtract a term ai. So I shift the origin from, so now the origin is only in terms of x's, okay? So x1, x2 up to xn, from the origin being zeros, if I shift it to a1, a2 up to an, then that means that I'm looking at the graph of lambda 1 x1 minus a1 the whole square up to lambda n xn minus an the whole square, right? Now, when I expand all of this out, all of those ai squares along with lambda I squares, they will just contribute to the constant. The constant will change somehow. But I will add a linear term, But conversely, if I have a linear term added to the standard form, then this says that I can go backwards. So let's just write this down. So step 1, getting rid of the linear. Getting and this is very simple. Complete the square. So if I just have something like lambda 1 x1 square plus lambda n xn square, and this linear part, remember what we had, the p times x. So that means it will be of the type p1 x1 plus up to pn xn plus constant. So I'm just going to say constant, all right, it's going to be, so what is this going to be? This is going to be lambda 1 times x1 minus k1 the whole square plus up to lambda n times an ups xn minus an the whole square plus another constant. Where, what do we have? So we can just say, right? I mean, so this, yeah, so just help me over here. What is the linear term involving x1? That is going to be minus lambda 1 minus lambda 1 times 2x1. Let's just do this in terms of I. Minus 2 lambda I ai, that is going to equal pi. So take ai equals, yeah, what? Minus pi divided by 2 times lambda I. Okay. So now, of course, there is an issue over here. What if lambda is 0? In other words, that variable doesn't even occur. See, if x square is not there, let's say x and y, x square is not there, but some linear term of x is there, I cannot get rid of that, no matter how I complete the square. Right? But let's assume that in our case, when we are going to be dealing with a Hessian, let's just assume that it's going to be, a non-singular Hessian. Right? So assuming lambda I not equal to 0. Okay, so this is easy, and we can do this in general. But the more interesting case is what happens in general. So in general, now that means I have this entire form, which is to say the function is x transpose times a times x, where A is this matrix of aij's. So of course I can write this as aij's, and I'm going to say aij equals aji. It's a symmetric matrix. Because remember, when I write a quadratic polynomial, I'm not going to write a separate term x1, x2 and a different term x2, x1. Right? So when I have a quadratic polynomial, the way the matrix is going to come is automatically going to be symmetric. It is just because the way I will do is that the coefficient of x1, x2, I will put half of that in the A12 term, and then the A21 term will be exactly the same, right? Okay, so the virtue of writing it in this form is that now that the matrix is symmetric, I know that I can diagonalize this matrix by means of an orthogonal matrix. So let's do that. Let's change basis. What should my new basis be? See, the original vectors, so the coordinates of the point that I'm taking, x1 up to xn, they are coordinates with respect to the standard basis, e1 up to en. Now I want to express these xi's in terms of a new basis. What is the basis with respect to which I should express this vector? And
the eigenvectors of
Exactly. So notice what I did over here. I just want to carry out exactly the same thing. So with this in mind, let us try to understand what the let's try to see the example. Okay. So this example number 4, let us try to carry out in terms of the general language. So here, let's write this down. Here, what is A?
0, half, half 0.
Correct. 0, half, half 0. Okay. What matrix is this? Or we can just, let me just change this here. Okay. Because I don't want to have this half cluttering everything. So I will just keep it as a half outside. Okay. What are the eigenvalues of this? Or more to the point. So ignore the half. The half is only going to scale the eigenvalues. The eigenvectors will stay the same. It is the eigenvectors that I want, right? Because those are going to be my new basis vectors. So ignore the half. Then this is just something that switches x and y coordinates, right? As an operator. So what are the eigenvectors of that? It's just reflection in the line y equal to x. So the eigenvectors of this are going to be, well,
1 by root 2, 1 by root 2, and
right, exactly. Correct. So you're normalizing it, but eigenvectors, you can just first take them to be 1, 1, and then 1 minus 1. And you see that's exactly where those u and v are coming from. I'm writing x and y in terms of new quantities u and v as vectors, right? I've just normalized those vectors. So I'm going to carry out exactly the same procedure. So eigenvectors are 1, 1. So normalize them, etc. Okay, so let's carry this out. So in general, we express x in terms of new basis consisting of eigenvectors of A. So, of course, A is symmetric. Therefore, all of its eigenvalues are real and it can be diagonalized. But more to the point, there is an orthonormal eigenbasis. Orthonormal eigenvectors of A. All right. So, let's carry this out. So, remember in linear algebra, when we diagonalize a matrix, not when. Diagonalizing a matrix A. So what does that mean? It means that I write diagonalizing a matrix A. So that means that, let me follow the same notation. Gamma is as Professor Pramath. So that is D, or in other words, this is really the same thing as A gamma equals gamma D, right? So gamma equal to the columns of gamma form an eigenbasis, correct? eigenbasis corresponding to matrix A. Right? That's what it means to diagonalize. And this equation here, really notice that A gamma equals gamma times D. That is precisely expressing that every column of gamma is an eigenvector whose eigenvalue is going to be the corresponding diagonal entry of the diagonal matrix D. That's exactly how matrix multiplication works. Okay, so here gamma is orthogonal. It's an orthogonal matrix, which is to say gamma transpose equals gamma transpose gamma equals identity. That precisely says that the columns are orthonormal. Okay, so what gives? Let's just do this. And I have, as a result, gamma transpose A gamma is equal to D. Okay, so let's use this in the equation. So I'm just going to write down the earlier equation. So what was phi of x? That was equal to x transpose AX, and then the rest of the parts. Okay, so let's just carry those. So P is a row vector, X is a column vector, plus some R. Okay, very well. So what am I going to do? I'm simply going to substitute. All right, so maybe even before this, we should sort of answer this question. So I said we are going to express this X in terms of new basis consisting of these eigenvectors. And the matrix that these eigenvectors make, when I list them in some order, is gamma. So picture X as a column vector. The coordinates of the entries of that are basically just the coefficients of X when expressed as in terms of standard basis. Question: what will be the coordinates of X when I express them in terms of the eigenbasis? So I'm going to say X star, or let coordinate vector of X in terms of new basis consisting of columns of. So of course, there can be only two possible answers to this. The column vector X star, that is a number of coordinates, will be obtained from the column vector for X by multiplying it by either gamma or gamma inverse, which is the same as gamma transpose. Which one is it?
On the left by gamma inverse.
So let me write this. So what is X star in terms of X? Do I put gamma here or do I put gamma inverse?
Gamma inverse there.
Okay, and there should be no confusion about this. You see, it's sort of very simple. Suppose in my old units, the unit quantity was 1, right? And let's say I was expressing the vector 5 in terms of that. So it is really 5 times 1. Now, if I change my scale to be, I call my new unit vector to be 2, then the coordinate of what was earlier 5 will not become 10, it will become 5 by 2, right? Straightforward, no? If my unit becomes twice as much, then the coordinate will become half. So I have to multiply by the inverse. So this is gamma inverse of X, which is the same thing as gamma transpose of X. So this is the substitution. So substitute this. So use this in the formula for, and away we go. So what do we get? X transpose. So A is just going to work out to be I want to get this in terms of the diagonal matrix. So I will substitute for A in terms of D. So in other words, A is equal to gamma D gamma transpose. So X transpose, and let's substitute for X transpose. Okay, so help me over here. A is gamma D gamma transpose X. And of course, I'm going to group it like this. Plus P times X. And so I will just introduce. So you see this gamma, I want to get everything in terms of gamma transpose. So here I also want to have gamma transpose X times gamma plus phi. So this is what phi of X is. So that is going to be X star. Sorry, gamma transpose X is X star. So this is X star. This is X star transpose times D plus P gamma times X star plus R. And so I will give this a new name. So this is going to be some phi, let's say psi of X star. This is what the equation has now become in terms of the new coordinate X star, okay? And if if this becomes a bit opaque, then all you have to do is to go back at that example and look at that example where we just were able to transform between xy and x square minus y square. Exactly the same thing is going on more generally. But now look at this formula. So this is in the standard form, right? Because notice D is just the diagonal entry. So when I multiply this out, the diagonal entries of D are going to multiply the squares of the entries of the X star vector and get added. Plus linear term plus R. And now use step 1 to eliminate the linear. Okay. So any questions so far? Again, please do not be caught in the sort of formulas and manipulations. The thing to remember is this: there is very little that is going on. It's just this.
Sir, in the first step, we assumed lambda I not equal to 0.
Right,
That's
right.
just saying that it's invertible, right?
Right. Absolutely. So if you want to see in the second step, if some xi doesn't occur, all right. So just 1 second over here. So in the second step, did we ever need that the matrix A is non-singular?
No.
No, because any symmetric matrix can be diagonalized, right? I may get diagonal entry 0, that doesn't matter. So the second step is perfectly fine. So what I have highlighted here, this is really the point. That's all that is going. Okay. Use step 1 to eliminate the linearity, assuming that all the eigenvalues that I have are non-zero. Okay, so let's now go back and see more examples. More examples. And now you see, okay, so let's go back to the standard term to sort of complete the geometric description. So you see this standard form here, if all the lambdas are positive, then you see this is clearly going to correspond to the positive definite case. And I am going to have a unique, in fact, a global minimum. And that will happen to be that constant that is added at the end, where all the xi's are 0. Of course, by shifting and orthogonal change, a general case could very easily reduce to this. When all the lambdas are negative, then that's the case where I get a global maximum. And when lambdas are mixed, some are positive and some are negative, then you see that in different directions, then I'm going to get saddle points. So this form, the standard form, is sort of making things transparent exactly how this geometry is. In the basic examples, I took lambdas to be 1 or at least all equal. If they are not, then instead of a circle, I will get an ellipse, right? There will be some, stretching or bulging in, compressing or bulging in some different directions. But the qualitative nature will stay the same. Okay, so some more examples. And I will list some examples because we don't really have a whole lot of time. And you should absolutely work out these examples on your own. I'm taking these examples from Professor Pramad's lectures, but you will have more on the homework. The next homework is coming. Okay. More examples to work out. So let's just begin a new numbering here. F of x comma y equals x squared minus xy plus y squared. What do you think this is going to be? Should carry this out, okay? Then here was the example that I wrote last time. So 2x squared plus 3y squared. And by the way, the procedure above tells you how to generate your own examples. Start with a standard form, shift the origin, right? And then just apply some orthogonal matrix to, just do some change of coordinates to that. Just use some orthonormal matrix. And you will get a very different looking thing, but the underlying geometry has not changed. By the way, so one thing I should have stated. The graph of phi and then this graph of psi. Will the shape or maxima or minima, will anything be different?
Sorry, sir, could you repeat that?
So the question is now look at this phi. I can think of it just as a formula, right? In terms of x1 up to xn, which are letters, right? Now the formula that I have written below, the formula for psi, that is in terms of x star. But now I can just forget that this x star came from x. I can just think of those coordinates as some variables and write the new formula. The two formulas will be quite different. I am saying, will the graphs be essentially different in the sense that will their shape be different, or will the maxima or minima of one be different from maxima or minima of the other? I'm not saying where the maxima or minima occur, but the actual maximum or minimum values. And the answer is no. Why is that? Okay, so see in just 2 dimensions. That means that the input is only x and y, and the output is a third variable. So I can see this as a surface. The effect of linear change of coordinates, what is that? It is just as if you are picking up this and just moving it in a different place. So you can think of this either as shifting the origin or keeping the origin the same, but shifting the surface to a different place. Yeah, your address of where your maximum or minimum occurs will change, but the graph is going to look exactly the same. Now, the second step, which is the orthogonal change of coordinates, that is also unique. You see, in terms of calculations, it may appear more complicated, but it really is not. We saw that an orthogonal change of coordinates in the in the 2-dimensional case, what is it? It's a rotation or a reflection. So if it's a rotation, what have you done? You have simply taken, so now I have already taken care of shifting the origin if necessary. Or I can take care of it afterwards. So what have I done? I have simply taken this whatever mountain that I had, a model, let's say, and I have simply rotated it. The shape is not going to change in any way. Geometrically, it's the exact same thing. All the lengths and distances are preserved. So all that is happening is it's an orthogonal change. So nothing is going to happen in terms of only the addresses are going to change. But any relative distances or angles, nothing is going to change. All that you have done is you have put a different address system in order to make your life easier. That's all. If you do not want to think of turning the mountain, all that you can say, well, the mountain is staying the way it is, the topography. All that you are doing is you are turning your head. But only horizontally, okay? You're not tilting it. Heights are not changing. If you're looking at it from a plane, let's say, the plane has just changed direction. That's all. So your view will change, but the essential reality does not change. Okay, so let me write down the second one. Minus 4xy minus 12x plus 14y plus 21. So again, I have taken this directly, but you see, where does this come from? So just verify. So 2 times x minus 2 the whole square plus 3 times y plus 1 the whole square minus 4 times x minus 2 times y plus 1 plus 2. So check that this is the case. So you see effectively what has happened. The formula is simpler. I have gotten rid of all the linear terms. And this is purely quadratic plus that constant. So new origin is 2 minus 1. Let's put this in quotation marks. Okay. And then the third one is, it's a very nice example, x cube plus y cube minus 3x minus 3y. So I'm going to say beyond quadratics. And also, you see what happens if I do x cube minus y cube. Let's say plus 3x minus 3. Okay. So we are almost out of time. Maybe we have just a couple of minutes left. So with this, I just want to stop for today's class. And but I will stay. If I strongly suggest that you stay behind and try to work these out using calculus as well as the quadratic part, seeing how to change the coordinates in order to get to the standard form.
Recording stopped.
And you will have a lot more practice. In a way, this is very nice because unlike the more theoretical part where we proved that all the epsilons and deltas and under what conditions are required for the second partials to be equal, what conditions are required for the function to be C1. Unlike that, once you have the theorems, here everything is very computational. So you can use examples to build intuition. Okay. So I strongly suggest that you work examples now. And anyway, homework will have enough practice. Once we finish this in the next class, then we will go on to, we'll see if anything else is required. It's not clear to me whether we need implicit function theorem. But we will go to Lagrange multipliers, more general optimization. So for example, for, in the one variable case, you cannot realistically say that your function is going to be defined always on an open set or your function is defined on the entire real line, or even an open set. You see, that is always the condition that we have imposed so far. You want to calculate the derivative, that means you want to have a neighborhood. But in practice, this is very often not the case. And very often what happens is that, okay, I'm just maximizing or minimizing over a closed interval. You saw that, right? So how does the situation change? I mean, for one thing, forget even derivatives or anything. If my function is continuous, defined on a closed interval, then I know that a maximum and a minimum must exist globally. Why? Come on, this is straightforward. A continuous function defined on a closed interval must have a global maximum and a global minimum, because in terms of concepts that we have seen, it's a straightforward thing, no?
A continuous function maps a compact set to a compact set.
Right. And if you really want to, so see, the thing is, now I'm going to change that closed interval, right, to a multivariable situation. So imagine that I have some function, and let's say the function is defined on R2, but I don't care about R2. I just want to say this is an enclosed region. Let's say some closed and bounded set, some compact set, right? Let's say the closed ball. I want to maximize this function over a closed ball. We have seen examples of this. Remember, when you have an operator norm, you are taking linear functions and you max, but it could be some complicated function. And let's say I want to maximize it over a closed ball. Then what should I do? You see, going by what you did over the real line. And we'll assume that the function is differentiable. Then there are sort of this breaks into two distinct parts, right? You do your usual calculus magic in the interior, on the open interval, and you identify candidates and you do a usual stuff, critical points, look at whatever test you want, and then you also look at the endpoints. So there's going to be some analog of that. But you see, if so I want to separately treat the interior of the circle, where I can use this method, whatever we did so far. Find critical points, look at the Hessian, all of that stuff we can do on the interior. But what are we going to do on the boundary? You see, I have to look at the boundary separately. In case of a closed interval on the real line, it was easy because it was just 2 points. I just had to. But here, I will have that entire circle. No? It is absolutely not necessary that any critical point be on the circle, on that boundary. Again, look at the one variable situation. So how do I do this? And the idea is the following. So one way to formulate the thing is that now I have two functions that I'm considering. One is the function that I'm maximizing or minimizing. Okay. But there is a second function which characterizes the boundary or characterizes the set on which I'm maximizing or minimizing. So in the case that we are talking about, it's the circle. So there is a second equation. So there is some equation that I'm maximizing or minimizing, some formula, but there is also the set x square plus y square equal to r. And we will see that that there is a way in which I can use. So there is the method of Lagrange multipliers, which allows me to handle this situation. All right. So I'll stick around for a bit if people want to work on this. But if you do not want to work on it now, then you should absolutely work on this at home. In the next class, I will just we'll just quickly see the answers, maybe do some more examples, and then go on to Lagrange multipliers. What is left in the semester is we are in reasonably good shape. What is left in the semester is following. So once we do this Lagrange multipliers, then the main things to do is this inverse function theorem and implicit function theorem. That is sort of making a small beginning in the direction of differential geometry. That is one task. And once you prove one of these theorems, then the other one is sort of follows from it. You can go in either direction. So that is one task. And the second thing is, in a way, this course is a course of many beginnings. In the beginning, what we did was we sort of did a little bit of topology. We did a little bit of non-linear spaces and showed various norms, their equivalent. That's, you could say that, okay, that's like a small amount of functional analysis. Then we did a little bit of topology. Then we did a little bit of metric spaces, etc. So you will see some of that in analysis 3. After that, we did differential calculus. That was the proper content of this course. So this inverse function theorem, implicit function theorem, that's a little beginning of differential geometry. And the final thing is, we have to see what happens when I apply these techniques where the variable is not a real variable. Variables don't take real values, but they take complex values. And that opens a whole new wonderful world in the direction of complex analysis, which is again also intimately tied to algebraic geometry. So the analysis there is much more rigid. It is, in real analysis, many pathological things are there. In complex analysis, you'll see that a function, if it is C1, it's already C infinity. That's it. So in real analysis, if something is expressed by a power series, then the function and the power series, they are related, but one does not, the power series may not determine the function everywhere. For holomorphic functions, no, the power series really is really one way of really thinking about the function. So we'll make a small beginning. So those are the 2 topics that will be left after this, and we have enough time. We may another thing. So officially, we are going to be ending the semester, I think, on what, 9th of May or something like that. Is that? Let me just check. Yeah, 6th of May, I think, is officially the last day of classes. We will finish the portion by then, but you are not going to be having exams the following week. The exams will begin only on the 18th. So I will conduct classes, and whatever you people want me to discuss, we will discuss some stuff. It will not be on the final. On the final, we will have only what is in the official syllabus, nothing else. But I think we will have a little bit of time left at the end, so we can discuss other things, provided I know about them. Okay. If you ask me to teach some hard analysis, then I may not be able to do that. Okay, so I'll stay as long as people are here, and maybe you can work on these.
So for these precisely, should we try to find the extreme points, or just
right? So okay, so 2 things, though. So one is for number 1 and number 2. There is this what we did today. By the way, I think this goes under the name of principal axis theorem. That effectively, in when you get this form, just the standard form, then those variables that you have, the x1 star, x2 star up to xn star, with respect to which it is just a sum of squares with positive or negative coefficients plus a constant. So those are the principal axes. So yes, so you can try to find the principal axis, but that is just linear algebra. Once you do that, then the max or mean is just sort of handed to you. You see. But you can also do it using the Hessian. So if you do not want to practice the linear algebra, then you can just do the max and min. And then that is using what we did in the last class, which is calculate the critical points by equating the derivative to be 0. That is the derivative matrix to be 0. And once you get those critical points, then find the Hessian matrix at those points and see what nature that Hessian matrix has, whether it's positive definite or negative definite or indefinite, and accordingly classify it as local max or min or a saddle point, assuming that the Hessian is non-singular, which I think it is going to be in all of these cases.
Okay, got it, sir. Thank you.
Sir, I had a question.
Yes.
So if you are given if you're given a saddle point,
Right.
and then we take the Hessian, and then we take it around uh, a direction, a particular
Right. A particular direction. Yes.
yeah, and then if you vary the direction continuously, will the the positive definiteness and negative, will it be continuous? So, sir, I felt this when I saw the graph of you showed a thing
Okay,
in.
let me, so maybe I should go to the, so let me stop sharing this and perhaps open that picture once again. Let's do that. Okay, so let me see if I can share that screen once again. Okay, so yeah, so here is the thing.
Yeah,
So
sir.
what you are saying is that, so the y direction is one principal direction where you have the max, where you're going like this, and that's a maximum, and the x direction is a minimum. So what are you saying, that I start
Yeah, sir.
moving other
We
direction?
take a vector, a vector, and then we rotate the vector along the about the origin, and then uh, first it will if you're starting from the uh, x-axis in the
Right.
anti-clockwise direction, then it first will be positive definite, then it will become zero, then it will become negative definite, and then it will become positive definite, and then it becomes zero again. And it becomes
No,
zero.
I'm so sorry. I want to understand what do you mean by it?
It means the bilinear form
Okay.
defined by the history.
Yeah, but you see, okay, so one thing is that the Hessian is going to give you some information only at the critical point, right?
Yes, sir.
Right. So the Hessian at the critical point is okay. So now I'm a bit confused over here about. You see, the Hessian is going to be neither positive definite nor negative definite.
Yes,
Has
sir.
a positive eigenvalue as well as a negative eigenvalue.
Yeah.
But if you think in terms of bilinear forms, again, you see, the bilinear form, sometimes it will take positive values, sometimes it will take negative values. So,
I wanted to put somehow that is continuous.
so
Yeah.
what is continuous?
Sir, I don't know, sir. It's not forward.
So we have to know,
Yeah.
but let's see. Vague questions are good because there is some kind of idea. Now, if you think of the Hessian itself, are you varying the point, or are you keeping the point fixed but varying the direction? What is it that you're doing?
Keeping the point fixed and varying the direction.
Okay, so if the point is fixed, then the Hessian at that point is in the quadratic case, you see the Hessian is just a constant matrix. Of course, if you're, by the way, so sorry, there is another thing. Sorry, I'm also getting a bit confused over here. In the quadratic case, even if I vary the point, even then the Hessian is constant, you see. Because when I take the double derivative, everything, I mean, all the letters go away, it's a quadratic. So even if I vary the point, the Hessian is constant. That is a separate issue. But you're not talking about that. You're anyway staying only at one point. So at any given point, the Hessian is just a constant matrix. Okay. So what now? But somehow what you want to do is that you want to wait. So in a way, what you're doing, I think, is that you are taking different directions. You're slicing this graph in different directions at a time.
Yes.
Right. And if I do that, then every time I will get a different shaped cut.
In some direction, we go the function will always decrease, and in some direction, the function will increase since it is saddle point.
Yeah, right.
So I want to prove that it's something like continuous or something. I don't know.
Yeah. So what? Okay. If you want to talk about continuity of something, then you have to specify what quantity it is, right? In order to make it a more precise But the variation is, I think, definitely going to be continuous. I mean, this is a smooth function. So
The C2 function, it will be maybe.
yeah, but what is it? You see, again,
Yeah,
this
yeah.
is the
Yeah,
so
it.
somehow. So the way I'm understanding your question is that if I take all of those cuts, I take a knife one at a time and I cut this surface in different directions, and I look at the and I look at the shape of the cut, which will just be a curve. Then the way I'm interpreting what you're saying is that these curves themselves vary in a continuous fashion.
Yes, yeah, I
Right.
think so. Yeah.
Yeah, but and I'm sure there is a way to make this precise. What does it mean that curves vary continuously? We are now talking in a different space, you see. I'm talking in the space of functions here. You're talking about deciding continuity in the space of functions.
Yes, sir. Yes.
Okay, and you can do that. I mean, so that's what functional analysts, they do this. So what norm? So let us say you have you have functions of real variable. What norm? Then you can put a norm on this. Let's say these are bounded let's say these functions are bounded. Then you can put a sup norm on it. Continuous, let's say continuous functions on a closed interval 0, 1. If you have, then you can put a norm on this. Or at least you can okay, let's say you can at least put a metric on it. The distance between two functions is the sup of the difference between them, pointwise difference. So you can do various things, and under suitable notion of continuity, it is clear that these functions are going to vary continuously.
Sir, like, is this related to moduli space or something? Because like we are parameterizing with respect to sphere about that.
Yeah, so moduli space definitely means that you do parameterize things, but I think over there, in algebraic geometry, when you want to okay, a very simple, see, typically when you say moduli space, what you want to do is you want to give a geometric structure to whatever family is varying. The family may itself is often geometric, okay, but I want to give a geometric structure to that family. And a very simple example is that if I take, let us say I take all lines through the origin. So let's see the projective space. If I take, or first a simpler example, let us suppose I take the set of all directions in the plane, that is direction vectors passing through the origin. Now those directions, that's not a I mean, the set of all directions by itself, as it's stated, is not a geometric object, but I can very easily make it into a geometric object, right? That for any given direction, I parameterize it by the place where it intersects the unit circle. And so I can say that the set of directions is really the same as the unit circle. And this somehow corresponds, no? If I shift the angle slightly, if I just rotate it slightly, then the corresponding point on the unit circle is also close. So this corresponds to my intuition. So you can say that the space of all directions is parameterized by the unit circle. But then life gets more interesting if I say, no, I don't want to parameterize directions. I want to parameterize lines through the origin. That is all one-dimensional subspaces of R2. Then you see it is no longer circle, because this line will intersect the circle in two places. So it is the circle with diagonally opposite points identified. But topologically, that is also a circle if you see it, because for each one of these 2 points, I can just take the point in the upper semicircle, let's say. So I can just drop the entire lower semicircle. Except there is a problem, no? Where I have the diagonally opposite points on the x-axis, they are still represented by 2 different points, but I want to identify them. So I just put those 2 points together. So it's the upper semicircle with the endpoints identified. So it's again a circle. Now, if you do this in 3 dimensions, then life gets more interesting. I get the hemisphere, but now on the equator, I have to identify diagonally opposite points. That's not something that you can visualize easily, but you can say, so this is the real projective space of lines in 3 dimensions. And it also is a geometric object parameterized by whatever I just said. And it is a manifold. It's a beautiful manifold. So you can do geometry. So to say it in short, the idea of defining moduli spaces is to take a family of geometric objects or family of objects, often geometric, and regard that itself as a geometric object and try to do geometry on it. Like, okay, is it connected? Does it have some holes in there? What is the dimension of this, etc.
Okay.
So in this case, we'll defining all, let's say, the continuous curves on this surface, that there's probably no nice geometry that it forms, but we can do analysis on it, is what you're doing.
Yeah, we can certainly do analysis on it. But notice here, I mean, the question as was asked was much more limited in scope. We are not taking all curves. We are taking only those that pass through a line, but that are obtained just by a straight line cut of the knife. That's all.
Straight line as in like relative to like the surface, the straight.
No,
like
no. I mean by straight line, I mean it just cutting, just taking on, just limiting to a direction vector. That's all. That's what I meant. That you are cutting it with a vertical stroke. Parallel to the Z axis. Oh, sorry, not parallel. Basically, this knife should pass through the Z axis. But of course, it can rotate around the Z axis. Yeah, it is kind of a bit hard to visualize, no? So what will happen? So that point which is a maximum, then it will become a minimum. But in between the curves, how are they going to be? In the
So I guess they would be parabolas which like keep widening and then they become a flat line and then go down
yeah,
again.
so it's not clear that it is ever going to be a line. No, I don't think that there is there a line on that surface, a straight line?
I think x equal to y, we get 0 identically.
Right. So x. Right. So so right, exactly. We get identically 0 over there. So yes. So can I find a view where that is? Oops, sorry.
Here, I guess one way to think maybe there is a blue line which was the blue the thing. There seems to be a line of blue along x equal to y.
Sorry, 1 second. So okay, so can we maybe do something like this, or how? What would be a view that is? See, okay. So the other thing is I have not played with this enough. The way you see, the way there are lines drawn on this, you see, those are only drawn in the direction of the principal axis. Do you see this? These lines?
Yes, sir.
That grid that is there, but it should be possible to to get the computer to draw this grid in whatever directions we like. And that may be helpful, right? So I guess this is what if we do, right? Something like this, maybe. Yeah, Um, so the question is, here's the question. Suppose I do this rotation. Is it true that until I get that straight line, x equal to y or x equal to minus y, it's always a parabola? It is just that it is going to keep getting wider and wider. So the way I'm thinking of it is, I'm first starting with in this direction. So I have an upside down parabola, a maximum. And as I keep going in these directions, so first here, then here. So at this place, somewhere like that, I'm going to get a horizontal line. Until then, is it going to be always parabolas that just keep getting sort of less and less steep? That's the way it seems, right? And then when I go further from it, then I will get parabolas that open up. Is that right? Does my question make sense, by the way?
So do you mean as you vary x as y times m, let's say,
Right.
where m
Always in the direction of direction vectors. Yes, absolutely.
and so when m becomes 1 or tends to 1 or
Correct.
minus
So
1.
yeah, correct. So in fact, that's exactly right. So thanks for pointing that out, because it's a very easy question to answer. Because if I just put y equals lambda times x, then just see what the graph becomes, right? It's always a parabola. So it becomes what? So y is lambda times x. Then you are just going to get x square times 1 minus lambda square. And that just completely settles it. Of course, it is going to be a parabola. But the leading coefficient, that 1 minus lambda square, that as lambda varies is going to is going to keep changing. And of course, when lambda is equal to plus or minus 1, I'm going to get identically 0, the value. But sometimes it will be a positive coefficient and sometimes it will be a negative coefficient. And depending on that, you will get either a parabola opening up or opening up. So that was easy. This also answers the question as was originally asked, that in a way I can see this. So you see, as you're varying the direction, then the directions are precisely the directions, you can say, they are encoded by this number lambda, right? The slope. And you see that as the number lambda is changing, these parabolas are changing continuously. Namely, you have this whatever 1 minus lambda square times x square, no? As lambda changes continuously, this thing is changing continuously. So you are able to quantify the continuous behavior.
Yeah, sir. Like I think, yeah, I got the answers.
Right.
So the question I asked.
Okay, good. So if there is, did anybody actually work anything out? Do things work out easily? Yeah, so if you did not, it's already past 1:30. So maybe we can stop if there are no questions, but please do work out, okay? This is all sort of now algorithmic. It's a recipe. So it should not be too difficult. Okay, so if there is nothing else, then we'll stop. Expect homework, and we will continue on Wednesday.
Sir, can I say one more thing?
Yes.
Yeah. So like, if we are given the Hessian, since V transpose HV is continuous function from V to R.
Right.
So if we take F inverse of open interval 0 to infinity, then it will be an open set. And F inverse of minus infinity to open interval 0 will be an open set.
Okay. So let me try to understand what you're saying over here. you're looking at the function.
V2 R given by
Correct.
V transpose HV.
Correct. Basically, so I think what you're trying to say, let me see if I understand this, is, yeah, just 1 second. Okay, so let me again let me stop sharing this and again go to. So as I understand what you are saying, what I think you are going to is that think of the Hessian positive definiteness not in terms of eigenvalues, but the function itself.
Yes, sir.
Right. That is that x goes to x transpose hx. And if the Hessian is positive definite, then this function will always take only positive values for non-zero vectors. And similarly for 1 second. Yeah, right. So this is, we already used this yesterday. So your point is that consider this function, and now what?
Yeah, so if the pre-image of the positive values will be strictly positive values will be an open set, and
Yes,
strictly negative will also be an open set.
correct. So there is a region in which there are some values of x for which this will take positive values, and some open set, possibly none, right? Possibly empty, where this will take negative values. Right. And in an indefinite case, both of these will be non-empty.
Yeah, so like
as we saw in this situation, right? Because in this principal directions are cases where if you go along those directions, then this function is going to take positive value somewhere, negative value somewhere, and then there will be a whole open set based on the observation that you just made. And the transition points is where it will take zero values. Right. So sorry, I mean, was there something more you wanted to say, or just
no, sir, like I want something kind of connectivity or something. Yeah, it does not work well.
But I'm not sure what you want to get out of this.
Yes, sir. Yeah.
I mean, so if so the variation between positive and negative values passing through zero, I think that is okay, that it will have to be very continuously, because this is a continuous function. But more than that, I cannot really, you see, if you want to say that, oh, by the way, if you want to say that, okay, the part where it is positive and the part where it is negative, they will sort of be, both of those will be connected regions. That is not necessarily true, because it may go from positive to negative to again positive to negative in many different ways. So especially if you think of a multivariable situation, there may be different positive and negative directions, and the variation between them may, it's not at all clear to me how whether you can say anything of that kind. But sorry, I don't know if I'm misunderstanding you, because
no, sir,
we don't have a precise question at hand. So
yes.
Okay, so any other observations? By the way, I'm very happy to have observations, questions, etc. Because every observation or question comes, it's only going to sort of show the enormity of my ignorance, and it's good to find one's ignorance, because then you can try to fill it. All right, so good. Let's stop for today. But please remember one thing. If you have any particular idea about what you would like us to discuss at the end of the semester, then you can think about that and let me know. Because especially if it is something that I do not know anything about, then I will have to prepare. You see, I can't just do it on the spot. So, okay, let's stop and we'll continue on Wednesday.
Thank you, sir.
Thank you, sir.